Hello everybody and welcome to this presentation. My name is Federico Bertagna and today I'm going to show you a research project I developed together with my colleagues Pierluigi and Patrick Ohlbrock. The project is about the conceptual design of three-dimensional structural and sun shading facades supported by machine learning, and it is based on a design framework previously introduced by the authors. In this presentation, we will introduce a fundamental feature within the framework, that is the possibility of working with variable topologies. Facade design is a multidisciplinary process that involves qualitative and quantitative aspects belonging to diverse disciplines, such as architecture, structural engineering, and building physics. As you can see in this slide, facades can be materialized in many different ways, and choices made in the early design stage strongly affect the overall process. Now, this multidisciplinary process can be handled using a sequential approach or a holistic approach. Holistic design approaches are based on the establishment of mutual relationships between disciplines as the key towards a conscious use of material and energy resources. In the current work, geometry becomes the common ground between the disciplines involved. In a previous research work, we proposed a design framework in which the computer assists the human designer in generating, evaluating, and clustering large sets of design options thanks to the use of machine learning. This framework was tested on a simple case study in which the topology of the structure was kept constant throughout the entire set of design explorations. Now, the objective of this contribution is to extend the holistic framework for the multidisciplinary design of facades previously introduced, and in particular to use three-dimensional systems with variable topologies. The framework is developed within Grasshopper, a visual scripting platform widely used in computational design, and it consists of four main phases: generation, evaluation, clustering, and selection. In particular, the generation phase is based on the combinatorial equilibrium modeling, or CEM tool. The evaluation is carried out using Caramba 3D and Ladybug tools for the structural and solar-related analysis, respectively. Finally, the resulting design options are clustered using SumPy. Very briefly, CEM is a form-finding tool based on vector-based 3D graphic statics, which, starting from a given topological diagram, generates pin-jointed structures in static equilibrium. Unlike in FE software for structural analysis, where the geometry of a structure is one of the inputs, CEM, starting from the forces, generates structurally informed solutions. The multidimensional vector that describes a design option is a set of parameters and metrics as listed here in this slide. The self-organizing maps, or SOM algorithm, groups the options in the high-dimensional solution space and then arrange them onto a 2D map. SumPy is the algorithm used here. The framework was tested on a design explorations based on the Holcim building, a competition project developed by the Swiss architect Christian Keretz and the engineer Josef Schwarz. It is a mixed-use building in which the facade, in addition to determining the building's aesthetic quality, is explicitly designed to brace the building against horizontal loads. In this case study, we also included solar control as a further design parameter to be integrated in the design process. The generation phase involved parametric explorations using CEM, considering variable topologies. Such variations involve both the number of elements and the connectivity between the elements. The results are stored as multidimensional vectors in a CSV file. Variable topologies result in variable sizes for these vectors, thus excluding the possibility for a direct comparison between options. However, by calculating the higher order statistics of the different parameters, it was possible to describe each option in a synthetic way. Thanks to a simple script that automates the procedure, we were able to produce over 34,000 solutions. Before starting with the clustering, we can filter out all the unwanted solutions, passing in this case from 34,000 to less than 24,000 solutions. The sum algorithm organizes the remaining solutions in a 2D map. Each node of the map contains a family of solutions. Node 500, for instance, contains 8 solutions that the algorithm detected as similar among each other. At this point, we can ask the machine to show us only those solutions that comply with certain criteria. For instance, option A is selected among those options that show small values for total mass in combination with criteria related to the standard deviation of node's position. In this slide, we are comparing the 3 selected options in order to show the diversity both in terms of form and in terms of performance. The next steps include an extension of the framework towards an informed regeneration of solutions based on the selection, which in this case was determinative for the entire process. And finally, being able to reduce calculation time of solar-related simulations would help in achieving an even more responsive setup. This, similarly to CM in the field of structures, could be achieved through geometry-based methods. Thank you very much for your attention.